morning, everybody. Also, very warm welcome from my side. First, I would like to thank Estonia Enterprise and the Estonian Weather Service to organize this meeting. We're very happy to be here. And I will try to educate you within 2 hours to be not a meteorologist, but at least to understand a little bit how we use satellites for the weather services. Please interrupt me if you have any questions. I have 2 presentations basically to present EUMETSAT first, and then I go quite in depth in how we operate the satellites, how we deliver the data to our users, which is quite technical, which is important to understand for future business opportunities from your side. So I will be quite in depth into that because this will be probably a long way for you also to get into the business which we are having. And so if I'm overdoing, stop me, we break, you can breathe, so it will be quite detailed what I'm doing. Before I start, it's very important to understand, it's always my apology, if the forecast for today was wrong, it's not our fault. So this is very important to understand. We are not doing forecasts. We are just giving to all our member states a basic data set on which the forecast is based. So if anything goes wrong, talk to them, not to me. So we do our best always. So that's very important. So EUMETSAT, what are we? What is our primary mission aim? We are not a development agency like the European Space Agency. We are an operational agency. We are using ESA to fulfill our tasks. So our primary objective is to establish, maintain, and exploit European systems of operational meteorological satellites, taking also into account the requirements of the World Meteorological Organization, because all the countries are also in the WMO, which is a UN organization who sets up the basic environment for the meteorological service. And what gets much more important since, I would say, 10 years, the whole question about climate change. As you probably know, you can only make predictions about climate change if you don't look at the data of yesterday. Why in Germany we have a very warm April, we have nearly summer in Germany. This is climate change. You cannot say anything about that. You need a long data series to really depict if there's any changes. So this objective that we contribute, because we have these long data sets, to climate and detection of global climate changes is also new in our convention. So how are we set up? So basically, we're very proud to have more member states than the European Union. You can see that also Switzerland, Turkey, and some other countries are full member states in our organization. The whole idea bringing up EUMETSAT was if you want to have a meteorological satellite, which is quite expensive, one country alone cannot afford that, so they all put their money together in one pot to do that. And currently, we are nearly 30 member states. Estonia is a full member state in EUMETSAT since last year, which we're very proud of. So there are only 2 remaining ones. We are not talking about Cyprus, which is a little bit difficult. Probably you know Cyprus is divided between Greece and Turkey, so it will take some time for Cyprus to get also a member state. But we have nearly everybody on board in Europe. As I said, we are an operational agency, and that means we have very long-term commitments on our operational service. You can see, hopefully you can read the years. We have 2 different systems, which are what we call mandatory programs, and which I explain a little bit later what it actually is, from the geostationary orbit and from the low Earth orbit, which have different applications. And we always have to make sure with our member states that we can deliver every 24 hours a day, 7 days a week, so the full year the data stream, and it should not change. So how we do things, that we always have 4 to 6 satellites of the same setup in one program. So our programs currently are running between 20 and 25 years. And that is also very interesting for industry because it's not a one-off. If you are in the business with EUMETSAT, there was always follow-on. If you are in one satellite program, in one application, over the years, over 20 years, there's always evolvement of these applications. So it's a long-term commitment if you're once in with our business. So in the upper part, oops, here, In the upper part, you see the geostationary satellites. We are already now in the second generation, which we call EUMETSAT second generation, which goes up to 2026. We have launched the first 3, which are already in orbit. And the question is, why do we have to relaunch? As I said, I make you a little satellite expert. The problem is that we have to keep the satellites always in the same position, that the viewing area is constant. And to do that, the satellites are moving in the orbit, and we always have to relocate them. And for that, you need fuel. You have little thrusters on the satellites to keep them always in the same position. So the main service from us comes at 0 degrees. And after 7 to 8 years, the tanks are empty, you cannot keep it in the position, it just drifts away, and then you have to replace it. Or you have, I mean, what we have also failures on instruments, which also means we have to replace them. So this is the geostationary program, and what we are developing in the moment is the next generation, which is called EUMETSAT third generation, which is a 2-satellite system. I will give more explanations later. And this will run probably up to 2040. I always make the joke, I will be dead in that time when the last one is launched. So it's really quite a specific business. And then we have in the low Earth orbit, these are the satellites who are flying over the pole in 800 kilometers. We have the METOP system, or the EPS system, European Polar System. We have launched METOP A in 2006. We have launched in 2012 a replacement satellite, METOP B. And we will launch in 2018 timeframe the last of the series. And we are currently, and that's very interesting, we are currently starting a new program which have to be approved by our member states, which is called EPS second generation, where we replace the low Earth orbit system with a 2-satellite system configuration. In the lower part, this is what we call mandatory programs. So all member states who join us have to be in this program, in the first 2. They are mandatory. They cannot just say, well, I don't like this program, I don't participate. They have to be in there. But we have also optional programs. These are programs where there are observations which are very close to metrology applications, but member states themselves can decide if they join. And one which we have is called JASON. This is all about sea level rise. And I will explain later a little bit, also show some graphs about what we're doing there. So this is a system which is also depicted very closely to climate change. It measures the rise of the sea level to very high accuracy in the centimeter area, which is a clear signal if there's any change in the system. We are participating in JASON 2, and currently we're proposing, we have a program in the development which is called JASON 3, a replacement, and down here you see the future of these measurements called JASON CS, which were partly financed also by the former, what we called Global Monitoring of Environment of Security, GMES program from the European Commission. Now it's called Copernicus. So that's basically set up what we have. How are we financed? We are financed according proportion to the strength of our member states. So it is broken down according to gross national income. So Germany pays 19% of our cost every year, and it breaks down to the last little country or big country. So Estonia pays probably 0.1% of all the costs which are incurred in 1 year. So this is a solidarity between all European countries. The strong ones pay more, which are not so strong pay less, but all have the same benefit of the service. So this is nobody here, I think nobody is here from the weather service, because they're always frightened with these graphs. This is our financial planning, and you can see there's a big peak in the years in front of us, which is basically the reason why we have one development program, EUMETSAT third generation, currently being in full development cycle, and we are coming up with a second one at the same time. So the yearly expenditure goes up to 500 million. At the same time, down here you see our launch schedule for the next launches, and before the launch we always have to pay the Ariane 5 or Soyuz, which are quite expensive. That's why we see these peaks. I'm fully aware that all member states always complain about this peak, but I can tell you it always moves to the right. Because we have also delays in the development, which is quite normal. So as I said, we have two types of satellites, the geostationary orbit, which is very important for the forecast for what we call nowcasting. Nowcasting is the forecast between this moment and the next 8 hours. And the second system, the polar system, is very important for the numerical weather prediction. So if your weather service is telling you next weekend will be very nice, this is a result of a numerical prediction system. So you assimilate the atmosphere, you put measurements inside, and you predict what is going to happen. And the polar system is the main source to make these predictions very accurate. So here you see the globe. We have, as I said, in the geostationary area, the 3 geostationary satellites, which are always looking at the same area of the Earth. So putting something in the geostationary orbit, the speed of the satellite turning around the Earth is exactly the same speed as the Earth turns. So it always looks at the same part of the Earth, which means you have a very high temporal resolution. You get pictures and measurements every 2.5 minutes, whereas the low Earth orbit satellites are very close. They have a higher resolution because they're much closer to the Earth. They need 110 minutes to go once over the poles. They need 24 hours to cover the full Earth. So that's the fundamental difference. So for the numerical weather prediction, it's very important to have the whole globe measured, and not only part of it. That's why the LEO satellites are very important for the numerical predictions. So I hope this runs. It ran before, now it doesn't run anymore. And we will go back. Why is this happening? This is strange, it worked before. So I start with the right side. So this is the LEO system. So it takes 110 minutes to go over the poles. It's very close to the Earth, so the resolution is much higher, which we see from there. It takes roughly 24 hours to cover the full Earth. It's only on my screen that it doesn't run. And here you see the geostation on the left side. So the geostationary satellite turns with the same speed as the Earth. He always looks at the same area. You ask yourself why it is a rounded satellite. It's a very nice system. I don't know the English words. As children, we had these Brummkreisel, which you turn up and they turn by itself and stand still. That's the same principle. So he turns with 100 RPM per minute, and that's why he's very stable. So this is the whole idea of it. Okay. So, and as I said, we have also the polar system. And the polar system we are doing together with our US partners. So you differentiate with the polar system when the satellite actually passes the equator. So our system always passes the equator at 9:30. So when the satellite is moving over the Earth is turning underneath it, it always comes back at 9:30 at the equator. So this is what we call the mid-morning orbit. So basically we see the mid-morning when flying over the Earth. The US have a system which is called early afternoon, so they cross the equator at 13:30. So you have a full view of the Earth to different time scales. And there are also a very early morning satellite, which is a US military satellite at 5:30, which has you can imagine which application that has. So this is the differentiation between the different orbits. And with NOAA, which is our most important international partner, we fully exchange all these data. So the Weather Service has the data from the 30:30 orbit and from our orbit to put the things together. So how basically we do our job? We have a ground segment in EUMETSAT. We have antennas spread over different sites where we receive either the data from the geostationary system, from the polar system, and from JSON, which are pre-processed in our headquarters. So everything, the antennas are outside, but all the processing infrastructure is in our headquarters in Darmstadt, which has a data center which archives all the data from the last 20 years. Then we generate the meteorological products, which are then disseminated to our member states. We have different ways to disseminate our data. We have one system which is called EUMETSAT, which is a DVB-S system, which is quite cheap, where all data are distributed. You can see here our receiving antennas. North of Frankfurt, we are in Usingen for the geostationary satellites and also in Italy. Then for the polar satellites, we have, because they go over the poles, we have one antenna system in Svalbard, which is also called Spitzbergen. Some of the news very up north, belongs to Norway, this island, where we receive our data. And now we have a service from the US out of the Antarctica, which actually allows that we receive the data earlier. After half of a revolution of the Earth, we receive our data from McMurdo, which improves the timeliness of our system. This is what I said before, what I call the EUMETSAT system, which is a DVB-S system. It's a very cheap system. You not just need a dish like for the TV satellites and a PC. And we have contracts with communication satellites who distribute these data over certain regions. So we see even a part of South America from our geostationary satellites. We have a big distribution over Europe and Africa. And now the Chinese are taking up also our data to distribute, which is called Fengyungcast, over the Chinese area. So everybody can receive these data. So socioeconomic benefits, very important. We are always, our governments always ask us, or you, also weather services, what's the benefit joining EUMETSAT? So it's quite an important question to answer. We are down here in the observation area. And from the top, from the forecasters and our member states, we receive the requirements, what we should do, which goes down here. And we deliver value upstream. So from the observations, it goes to the numerical prediction. Out of the numerical predictions, we have forecasters in the weather service who look at the results of the predictions, interpret them, and distribute warnings, or tell you the next weekend will be sunny, but don't stay too long in the sun because you get a sunburn, and all that is possible. And the climate areas or the prevention of disasters or being prepared for disaster, which is very important for all member states to manage severe weather events. You have these environment agencies who are responsible for that. So what are the main benefit areas for the forecasters? It's basically on the left side, which...
Sorry. Is that okay?
Well, I don't know. I don't see you anymore. Okay, I can read it. It's better now? Yeah. Okay. So here on the left side, safety of life and property and infrastructure. Transport is very important. Ship routing, aircraft routing. Aircraft routing and weather forecast for aircraft routing is one of the major income from all, I don't know how it's in Estonia, but for all weather services. It's the main income from the aircraft industry. Energy, agriculture. What we see all over Europe now, all the wind farms are coming up. So what is the evolution of wind in certain areas? Does it make sense to put a wind farm there? Very important also for solar energy and climate policy and protection. I just give some little examples. Obviously, there are much more. On the left side, you see this huge thunderstorm. Perhaps you remember that several years ago, a French aircraft crashed east of Brazil, flying through a big thunderstorm, which was not visible, how high he would be. This famous Airbus 350, I think it was. And you can reroute if you would have the data and know how high the tops are of a thunderstorm. You could have rerouted it. On the right side, you see the famous volcano from Iceland. I will not try to spell out this word, perhaps you can do that, which is up here, which I think 4 years ago brought down the whole air traffic over Europe. And we all realized how usual it is for us just to fly for 1 day from Frankfurt to London or whatever. So the whole aircraft traffic was brought down by the eruption of this volcano. And we could clearly see, and I'll show you some animations later, we could clearly see the ash cloud. We could not really, with the instruments which we currently have, estimate the particle size inside the ash cloud, but we clearly could calculate the distribution of the ash cloud. So there's still a lot of things to do in that area. Probably you remember that in summer 2010 there was huge fires in Russia. The Russians told everybody, oh, we have everything under control, and we could clearly see this in our satellites, how huge the plume of these fires were. Your colleagues from Finland were very much concerned about that, and if you have such a system, you can much more easily say, okay, this is the truth, don't tell us any stories. We can see in our satellites how these things are happening. Next one, this is more from Iceland, the distribution of the ash cloud, which was also clearly seen in our satellite data. So there are a lot of application areas. So we try to estimate the benefits of weather forecasting in the EU. And we're very conservative because it's always difficult, you're doing these things, I'm not an expert in that, to make this calculation, but there were huge studies done. If you only look at the minimum, so the benefit area for protection of property and infrastructure is between 1.3 billion per year up to 5.4 billion per year. Then the added value to the economy can go up to 41 billion per year. And the private use is also not small. So to be on the very conservative side, it's at least 15.5 billion per year benefit to the European community. And what we found out also in the study, what the study people who did that, it is proportional, the benefit is proportional basically to your GNI. So you can calculate out of that also what would be the benefit basically for Estonia, because it's proportional to the GNI. So I think it's quite a convincing case for investing in this area. Now I will try to make you a little bit how a numerical weather prediction system really works. So basically, the problem the forecasters have, how can they really predict if the next weekend is always my best example, but next weekend it will rain or it will be, temperatures will go down. How do they do that? So basically you need a model of the atmosphere. The better the model is, the better is your prediction. Then secondly, which is limited by the computing power of the model, the grid size. So the US are calculating every 80 kilometers 1 point. So in between you don't know. So the global forecast system, perhaps some of you probably know that, it's freely available from NOAA, gives you a prediction, but only every 80 kilometers 1 point. And in between you don't know. So there's a strong development in all weather service to have a higher resolution. What basically the weather service are doing, they're using a global model, which has a lower resolution, and using a high model just for the area. And the global model are the input to the high resolution model, which in some countries goes down to 1.5 kilometers. You can imagine countries which have a lot of mountains, like Switzerland. It's very difficult because you have small scale events in the mountains which are difficult to predict. So what really is happening, on the left side you see the state of the atmosphere, and then you add to the current model which you have, you add the observations. You look, what can I really measure in the moment in the atmosphere? Then you take these observations and put them into the model to improve your model for the current time. And out of that, you then predict. That's what we call assimilation. You take the actual values, look at your model, and see, is the model correct at that time, compared just with the measurements which you have actually done. So you tune your model to be really representative of the current weather. And then out of that, you do, at a certain time, a prediction. And this is the model forecast. And what is so important? To reduce the error. So if you look at the evolution of the forecast error of the last 20 years, Europe is at the front of doing that, the ECMWF, and I think Estonia is also a member of the European Centre of Medium Weather Forecast, which is in the UK. they're really the world-class forecast modelers, which are also doing, they have the same principle as we have, all European member states apart, they're paying, they're getting the forecast results. And what is important, that these, what you see on the right side, the satellite measurements are reducing the model error by 1/4. So if you don't have satellite measurements, then the forecast error increases by 25%. And that's why these measurements are so important. So the Weather Service not only have satellites, they also do, which you probably know, they have these balloons making in situ measurements of the atmosphere. And but the satellite data have a big influence on the forecast, and I can show you some examples. So this is the famous Hurricane Sandy, and we have one instrument on our satellite which is called a scatterometer. It's basically a radar which measures indirectly wind over the ocean. So you can imagine if you have no wind, you have a flat ocean, the backscatter from the radar is different than you have high waves. And because of the triangular shape of the antenna, we can even, out of that, depict the wind direction. And that's what a scatterometer does. And on the left side, you see the wind field, which was measured around Sandy. So what was very important for the US to be prepared for the landfall of Sandy, to predict that correctly when it will come. And you probably have seen in the news where it said landfall will be in 5 days or 4 days. So the operational forecast from EPS, from ECMWF here, you can see that they predicted 5 days before the area and the time when Sandy will hit the land, which is very important that you evacuate your people to get them away. If you remove, which you can do afterwards, you remove from the model all the satellite data, you can see that the hurricane really stays on the sea, which would be a complete wrong forecast. And afterwards, what you see on the right side is the verification. So if you compare both pictures, that's actually what has happened in reality. So the forecast 5 days before it happened was very precise. And if you don't have satellite measurements, you would have thought that the hurricane would stay over the ocean. So that really shows how important and what satellite can do for the forecasters. Okay, now I turn to our future programs. As we said, we have these 3 systems in orbit. The geostationary satellites, where we still will launch 1 satellite in the 2015 timeframe. The EPS, next one, METOP-C, we will launch in 2018. In JASON 3, we were planning to launch next year. So, and as I said, we have to replace that for the meteor third generation. This program is already approved. It's roughly overall with development, and it's quite a big number, but you have to divide that by many years, so it's basically a 3.4 billion program covering the full development, 24 years of operations, by all the launchers, all the ground segment, the recurring satellites, the contribution to the ESA program. So it's quite a huge number, but you have to divide it by 24 to see what is really happening each year. And what we are currently proposing, and is a 2 satellite system, so this time we have put the instruments, not everything on 1 satellite, but on 2 satellites. And I will show you a little bit later how we distributed the payload. And we will launch the first imaging satellite, which is a core service he has to deliver in the 2019 timeframe, and then a sounder satellite 2 years later, and that continues. So we have co-located satellites by 0.1 degree in geostationary orbit. And also we have to replace the polar system in the time frame of 2022 by the EPS 2nd generation. And this program is currently on the table for our member states to approve. It's also roughly a 3 billion program. And we need confirmation by our member states in the coming year. We will start that in the next council meeting to make a proposal for that. In the lower part, in the optional program, which I haven't presented before, there's probably heard in the news the Sentinel missions out of the GMES program, which is now called Copernicus. So last week there was a launch of the first Sentinel, which is a C-band radar, which is very important for ocean observations, ship routing, ice, oil spills. And there are 6 Sentinels. And we are operating on behalf of the European Commission these Sentinels, which are very close to meteorology, which are the Sentinel-3 mission, which is the ocean mission, which gives ocean color, ocean surface temperature. And we will operate Sentinel-4 and 5, which looks at atmospheric composition out of the geostationary and the low Earth orbit on our satellites. So how do we do that? That on the left corner you see the MTG, maybe the third generation program, the 2 satellites, and you see they look completely different than the ones which I've shown you in the animation. They're not anymore round. So these are 3-axis stabilized satellites. That's a very important step for us, which are new challenges to change the attitude control of the satellites. Why are we doing that? The main technical difference between the current meteorological satellites, the MSG satellites, you've seen, I've told you, they turn by 100 evolutions per minute. If you do a 360 degree in the geostationary orbit, you only see the Earth in 16 degrees. If you have a constant turn rate, you have only, like a photo, you only have a very short time to look at the Earth. And so you're limited in your resolution by that time. The exposure time, if you compare it with your photo, you can dial the exposure time, but our exposure time is constant. We cannot change that. But if you have low light, like a photo, you have to have a longer exposure time. And this allows you to do with this 3-axis stabilized satellite, because he continues to look at the same scene all the time. So you can have a much longer integration time. You can reduce the noise, you can reduce and improve radiometric accuracy. That's the whole idea, to change from a spin satellite to a 3-axis satellite. In the lower part, you can see the EPS 2nd generation. Also here, we distribute our payloads over 2 satellites. Some of you probably know the biggest Earth observation satellite ever built, the ENVISAT satellite, which ESA has built. And a spin-off out of that was the EPS system. If you put all your instrument on one satellite, and sometimes you have a launch failure, you lose everything. And therefore we decided, also looking at these risks, we decided, because we have a lot of instruments, we put them on 2 satellites. We distribute the payloads over 2 satellites. So if you have a problem, you don't lose everything what you have. And secondly, in Europe, this big platform to put 12 instruments on one platform is not anymore available. And we are hoping we're benefiting from the development of the Sentinels. In the upper right corner, you see the JSON-CS, the continuation of the ocean surface topography mission, where we look at sea level change. So what is very important to understand, what I said in the beginning, we are not a development agency. We are an operational agency. So we're using the European Space Agency to develop our satellites. And we use them also as a procurement agent to buy for us the recurring satellites. That's why our organization is not very big. We have roughly 550 people. Half of that are staff, the others are contractors to support us, because we don't want to go into this development area. So how is the flow of the requirements? So our council, which are basically you member states, set up the user requirements. You are telling us, which is a very long time where we consult our member states what they need in future. And we have to be very precise, because what you have seen in the schedule, the programs are running for over 20 years. So when you develop the next generation, you really want to make a qualitative step. It shouldn't be too big that you take risks, because it's operational, it's not a science mission. I mean, if ESA loses a science satellite, it's not very nice, but it doesn't hurt in a way. I mean, you lost your investment. But with us, if we lose a satellite because we are taking not mature technology on board, the services are immediately impacted. And that's why you have to balance your requirements against what you see coming in the future and what is mature, which you can really put operational into the orbit. and not try certain things which are not mature. That's very important. So this user requirements process takes up to 4 years with member states. They tell us what they need in the future. They tell us their priority, what is the most important application. And the most important application is always the nowcasting, the short-range forecasting for the next hours that you can issue warning with severe weathers. And then we set up all the user requirements, we set the priorities, and out of that, we then generate system requirements, which we give to ESA. So it flows down from us, from this level to ESA, on which then they define the statement of work for the European industry to develop the satellites. And the beauty of that is that ESA member states are very eager to, as I explained before, to join these programs, because normally ESA only builds one satellite. So, but if you are selected in the first satellite, you can be sure you also sell the recurring elements. So in the last 4 years, more ESA member states have have realized this benefit. Only the French industry was very clear about that in the former programs. Now we are the only program in ESA who gets more money for the program than ESA actually asks for. So that really shows the importance also for the industry. And then ESA delivers to us the satellites, but our responsible is the clear end-to-end system responsibility, from requirements to products. So we then set up the whole system, we develop the ground segment, we procure the launchers, we launch the satellite with Arianespace. Usually it's either an Ariane 5 for the geostationary satellites, or it's a Soyuz out of Kourou, or the future Ariane 6, whatever. And then we deliver over the full set the products to our users. So as I said before, just briefly, what is the METRIAL third generation? We have an advanced imaging capability. We have more spectral resolution, more spectral bands, which allows you to depict also fog very early in the morning and other atmospheric constituents. And what was very important was a major change to the current system, what we call rapid scanning. And I will show you an example of that, why this is so important. So the rapid scanning is basically the repeat rate of the images you get from the geostationary satellite. From the first generation, we only had pictures from the Earth every half an hour. From the second generation, we went down to 15 minutes. And we found out that the second generation can also do, it was not designed for it, a 5-minute rapid scanning. So every 5 minutes you get a full view of Europe. And for the next generation, we will go down to 2.5 minutes. And I'll show you some examples of that. At the same time, in the lower part, we have the first time, Europe is here, the world leader, the hyperspectral infrared sounding mission. It's a spectrometer in geostationary orbit, which gives you atmospheric constituents. So, you know, the whole discussion about pollution. The problem is to depict, if pollution comes into your country, did you produce it yourself, or did the wind bring it in? So to depict that, with satellites, we have to have a constant view on the area, which is currently not available. So, but from satellite, from geostationary orbit, this is possible. So you can really see how atmospheric constituents are moving over the continent. That's very important. And we also have an instrument from the Copernicus program, which looks at air quality. So this is what I said. This is actually, on the left side, you see the full Earth. That's a disk we are seeing from the 0 position over the equator. So you can see that we have a perfect view on Africa, but Europe is upper in the northern part. So we have to do some geolocation and rectification of the image. That the image that you see, you won't see it like that. You will just see it's flat. But this is possible with geometric correction. We see part of South America, and what is very important, I have better pictures for that, but not, I mean, I have hundreds of presentation material, I have to put certain things out. The hurricanes which are developing and going to the US coast are actually, where is the cursor, are actually developing west of Africa. So, and then they move over the equator to the US. So we are supporting NOAA because they don't have a satellite in this position. We are supporting NOAA in the hurricane season to see really how the hurricanes are evolving. So what we can do with the new system, we can, we can scan the Earth, the full scan in 10 minutes, and we can go with 16 channels, 1 kilometer resolution, and then we have a second mode which we call high resolution full scale imaging, and we can go down to 2.5 minutes with 4 channels. So here you can see the difference between the different, I hope it's visible. So the upper part shows you the 2.5, and here you see very strong overshooting systems in this area. At least I can see it on my computer, I hope you can also see it, compared to the lower part where it comes only every 15 minutes. And that's very, and here you see these little bubbles who are really shooting up very high in the atmosphere. And this is very interesting for the nowcasters to really predict if severe weather is evolving in thunderstorms. So this is the main improvement which we see with the new system. And then, as I said, we have also the Sentinel-4 instrument on board, which looks at atmospheric chemistry, ozone, CO2, NO2, sulfur dioxide. Don't ask me what CHO is. I used to know it. I didn't have time to look at it in an old presentation. It's a very complicated carbon